All right, so welcome everyone for our upcoming webinar, the this August webinar for the TRANS-IPIC UTC. My pleasure to be moderating this webinar here this afternoon. We have two amazing presentations from two of our very strong researchers. Um, I'm gonna start by saying a few words about our first speaker this afternoon, Dr. Mirian Velay-Lizancos. Dr. Velay-Lizancos is a tenured associate professor of civil engineering and Bowen Scholar of Excellence at Purdue University, where she also serves as the associate director of the PANCOL Lab. Her research focuses on high-performance, durable, and resilient cementitious materials and composites, as well as the development of novel construction materials with proactive effects during their service life and holistic life cycle assessment. She has received multiple honors, including the 2024 Young Investigator Medal from the Royal Academy of Engineering of Spain, along with the 2021 Outstanding Faculty Mentor Award. She's going to talk to us today about the projects she has been working with TRANS-IPIC on for the last, I would say, year and a half or so. The title is Optimizing CO2 Curing Conditions in Nano-Modified Cementitious Composites for Precast Applications. So, Miriam, the mic is with you now.
Thank you so much, and thank you for the great introduction. So let me share my screen. So can you see my screen now?
Yes.
Okay, just let me move this thing. Yeah, okay, perfect. So, well, good afternoon, everyone, and thank you for attending this webinar. Today, I will be just talking about some of the things that we did in this project and that we are doing. We cannot cover everything in just 20 to 50 minutes, 20 to 30 minutes, but I will do my best to show some of the highlights. So let me start from the very beginning. Well, this is the outline. I will start with just introduction, and then I will just highlight some of our main findings in terms of the combined effect of recovered carbon black and CO2 curing, and then on the role of the curing conditions on this combined effect. Finally, I will just talk a little bit about the future work and the things that we are doing right now. So as the motivation is clear, right? Just to give you an example, in the last infrastructure bill, half of this 1.4 trillion budget goes to just enhancement of the roads, bridges, and infrastructure projects. And that's completely normal, right? Especially thinking about concrete, which is almost everywhere in our infrastructure, has a lifespan between 50 to 100 years usually. So we built a lot around 100 years ago or a little bit less of that. So now there are many things that we need to rebuild. So our new infrastructure really demands improve durability. We wanted to do it even better than we did before. We need to reduce the cost because this is just too much money. And also we want to do it in a way that we will reduce the environmental impact so we can keep our mountains, keep our clean air and so forth. And one important, let's say, agent on this will be the precast industry. Why? Because precast production, which is an industrialized process, allow us to optimize the mixtures, use less cement, just have it more control for sure. Also, we are controlling all the conditions and everything, or most of them, so then we'll have a superior durability and also is more sustainable in the sense that we are reusing the formwork. It's also more economically sustainable in that sense. So it has many benefits, and we consider that the precast industry will play a big role on rebuilding all these things that we have to rebuild and also build new ones. And also this process, it just give us the opportunity of implement innovative approaches that require special conditions. Why? Because since this is an industrialized process, it's a controlled production. So we are able to do things in a much more precise way than in the field, and therefore we can implement innovative approaches in a greater extent. So related to that, there are two main approaches that we will cover on this webinar. One of them is related to using CO2 curing to enhance the mechanical properties, but also the durability of cementitious composites. CO2 curing is a process that in the field is very difficult to implement, almost near impossible, but it is a process that is feasible for some applications for precast elements. So that's one of the reasons why we want to look into that. The second approach that I will mention today is the nanomodification of the cementitious materials matrix, or in other words, how we can use nanomaterials or nanoadditives in general to improve the durability and the strength of our precast elements. Why we consider that nanomodification is kind of a very well approach for precast elements and for precast production is because nanoadditives can make a big, important, positive impact on the properties of the concrete. However, if you go a little bit, you put a little bit too much or a little bit too less, then the properties are not, or the effect is not as good as you might be expecting, or it can be even detrimental. Therefore, having a control environment and control mix is very important to get the best out of this technology of nanotechnology. So these two approaches are very well suited for precast elements, for precast production. One of the reasons why we were focusing on CO2 curing is because it is known that increases the strength. That's something that we know, and also reduces the the surface porosity and the water absorption. When the CO2 start to penetrate, it will start to carbonate the surface layer in particular. It's not going that deep, especially with CO2 curing, but in the surface layer will reduce the porosity, and therefore we might have good effects in terms of reducing water penetration and so forth. Now, in terms of nanomaterials, there's a lot of literature that shows that in the right amounts, both nanotitanium dioxide, for example, or nanosilica will enhance the strength, especially the early strength, which is important for, it's very important for precast element production, because if we want to do it in a cost-effective way, we need to accelerate this process in a way that then we can remove the formwork or transfer the loads if there's any pre-stress or so forth. So now, again, we are thinking about these two approaches because we want to improve durability and reduce costs. Reduce costs is also related to increase early strength, because if we increase early strength without increasing amount of cement, then we are having a product that will be cheaper, right? So we have to focus on these two things of our motivation. So now one question can be, what if we combine these two approaches? Will be just having the two positive effects together. They will be a little bit less, or it could be even higher, greater than adding the two of them. That's an important question, because sometimes even if there are two approaches that are positive, when you combine it, they might not be as positive as each of them in a separate form. So there is some research that we have done in the past related to the combination of CO2 curing and the use of nanoparticles, in particular in this case was nanotitanium dioxide. So here what you are saying, what you are seeing here is just, in blue is just normal curing mortars with no titanium dioxide or with different, is it sharing the screen? Can you see my screen? Well, I hope you are. Okay.
Yes, we can see the screen.
Okay, I think my computer did something weird. So with 0, 1, sorry, 0%, 1, 0.1, and so forth. 0.5, 1.5, and 2%. So we see that the use of titanium dioxide increases the strength, nothing new. And if we do CO2 curing with no titanium dioxide, we have an increase. Now, if we put 0.5, we have a similar increase, and now it's lower and lower. So we have to be careful, because adding these two approaches together is not just adding the two benefits together. Having said that, especially in this case, when 0.5% of titanium dioxide, we have the highest value, which is much higher than just not using titanium dioxide and not doing CO2 curing. So what I want to show with this, or what I wanted to mention, is that the benefit of these two treatments or these two approaches simultaneously, it just really depends on other variables, and the optimization of the process to combine the two of them to get the best of each of them is very important. So that's one of the needs, optimization of the mixing process, mixture, and also on the process. But not only that, these materials that I was just talking until now, like nanotitanium dioxide, nanosilica, they are quite expensive. And the production of these materials requires a lot of raw materials and energy. So it's not very efficient. So now another question could be, what could be an alternative? And especially an inexpensive alternative. So that's why we look into recovered carbon black, which is inexpensive and therefore might be a good option. Now, carbon black, just for those who don't know, is just waste that comes from the pyrolysis of the tires. This is recovered carbon black. Is not the carbon black that you use for paints and tires and so forth, that is more pure and more expensive. Now, again, we focus on our motivation, more durability, reduce costs, and for that we need to optimize the mixtures and find inexpensive additives. So now there are a lot of objectives. We will not cover all of them, as I said, because of the time, but I just want to mention the potential. We will assess the potential use of recovered carbon black as a nano additive, and I will just mention some of the issues that you might have and how to deal with them. Also, we'll talk about the compatibility of recovered carbon black addition and CO2 curing to get better properties, especially at early age, to speed up the process of production in precast elements. And finally, I will talk about how to optimize the conditions, the curing conditions, to get the best on this combination, and a little bit about corrosion resistance at the end too. So regarding the effects of recovered carbon black and CO2 curing together, well, this is the carbon black that we use. It's very hydrophobic. In the video, I think you will see that it's not mixing very well. It's not mixing with the water. It's just floating around. So that's why if you try to do it in dry, that will not work. And we have to first disperse it into the mixing water with a high shear mix. So that's something that we have to consider. Then what we did in the first studies that we were focusing on is the beginning pastes and mortars with different percentage of recovered carbon black and no carbon black too. And then we did several testing. So we did, well, the slab fresh properties for sure, and then we did also icy. But then with the hardened properties, that these are the ones that I will mention right now, what we did was just first keep the samples in the molds, do some pre-curing, and then half of the samples of each mixture will be air cure, while the other half will be CO2 cure. And then this is just for a period of 12 hours, and the rest of the time until testing, they are kept exactly on the same condition. So the only difference is here. And then we will test at 3, 7, and 28 days. We did the TGA, and also we did compressive strength test, and among others. And what I want to show you, just to share with you some of this data, is that first, if we focus only on normal curing, meaning no CO2 curing, that's what I mean, we can see that the use of carbon black increases the 3-day compressive strength, which is great, right? Because we wanted that. Now, in addition to that, when you do CO2 curing, you will see that you have an increase. The increase is not as big with recovered carbon black, but you are exceeding the one that is just reference and CO2. So what we are seeing is that if we combine CO2 curing and recovered carbon black, we will get the highest value, especially with 1%. And we are talking about an increase of 40% or so. So using these two things together, it just can really give you a much greater strength, early strength, and therefore you will be able to remove the forms earlier or transfer the loads earlier, and therefore you will have a much better production, like better production. Now, why this is happening? Well, there are many reasons, and I cannot go through all of them, but I just want to highlight one thing. This is the calcium carbonate of the samples 3 and 7 days, and you will see that when we are talking about yes, no CO2 curing, the amount of calcium carbonate is kind of the same for all of them, even it's lower for some of them with recovered carbon black. So there's no much of a difference of using carbon black when you have yes, no CO2 curing in terms of calcium carbonate content. So we are not adding calcium carbonate content. That's what I want to say. However, when we check the results of calcium carbonate content with CO2 curing, we will see that when you have recovered carbon black, the amount of calcium carbonate is greater than in the reference one. All of them are CO2 cure. And therefore, what we are seeing is that the presence of recovered carbon black fosters the calcium carbonate development in presence of CO2 curing. That's relevant, especially because we observe that that's not related to increasing the carbonation depth, it's more related to the amount of carbonation on the surface layer that you will see later on in the next part. So some takeaways here on this first part is yes, recovered carbon black, yeah, increases the early strength of materials. I didn't show all the data, but particularly when we have low water to cement ratio, we have greater results. And then other important things is just CO2 curing can enhance the benefits of using recovered carbon black. So we are adding additional strength, so therefore we can leverage the use of the two of them together, especially for lower amounts of carbon black. When we go to further, as you know, as it happened with other nanomaterials, if you put too much, then you will have a detrimental effect. So we have to be careful with that. And it decreases and recovered carbon black increases the calcium carbonate at early ages on the surface. Now, I want to move on to show you new things that if you have already been present in our previous presentations, you didn't see. So new things happening, which are related to the role of the curing conditions on this combined effect. Why? Well, the main reason for this is that we are talking about the industrial process, precast process, and therefore we can control humidity and temperature. So you will see, especially talking about humidity, that we can change a lot the combined effect of recovered carbon black and CO2 curing depending on the relative humidity. So that's an important thing to consider to optimize the process. So again, this is the recovered carbon black, which is not 100% pure, as you can imagine. That's the reason why it's called recover. Well, the reason is because it comes from tires, but it has a little bit of impurity. And what we did is we did mixture. We make mortar mixtures at the beginning with no recovered carbon black, with 1% and with 2%. Now, we wanted to optimize the process, so we need to check a lot of variables, right? To be able to see all the potential cases scenarios and then get a model to give us the response we want, which is what are the best conditions. So for that, we cure all the samples in the same conditions, except this small period of time where we will change humidity, temperature, and percentage of CO2 too. So in total, we will have 16 different curing conditions that we will test, and 9 samples per curing condition, 3 per different mix. Therefore, we are talking about a total of 144 samples, 28 per mixture. And then we will then test it at 3 days to see how it affects the early age properties, especially compressive strength. So what conditions are we talking? Okay, so here you can see the matrix. We are talking about no concentration, no CO2 curing, 0%, 5%, 10%, and 20% CO2 concentration. We are talking also on different relative humidities from 0 to 100, and all of that cure at 23 degrees C. In addition, we want to add also 100% relative humidity and curing at 50 degrees C, because some precast companies use high temperature to speed up the process. We want to compare CO2 curing with no heating versus, especially with no heating versus the one with heating, no CO2. So we are almost finishing. We have all the data on the green ones. Once we finalize all of them, that will be pretty soon, we will do the model. But I want to show you at least some of the findings we have so far, which I think are pretty interesting. So let's go ahead with that since we have limited time. So here you can see the compressive strength. I am showing just 0, 5%, and 10% CO2 concentration. And one thing that you can see is that with 1% recovered carbon black, always in all cases, we have a higher strength than with no carbon black. So 1% carbon black increases the early strength. But not only that, if we focus on no CO2 curing, no carbon black versus let's do 1% recovered carbon black and 10% CO2 curing, you will see that we are having an increase on the compressive strength of 26%. And we are talking about quite inexpensive way to increase quite a bit the early strength, compressive strength, I will say. And this is not related to increasing the carbonation depth, because we can see that if we get, for example, the 10%, so it doesn't matter if you're talking about the reference 1% or 2%, we have very similar carbonation depth, and therefore this is an increase of the carbonation depth is not explaining this jump. But this is just some of the results with 70% relative humidity. Now, if we go and show you now the results with 50% relative humidity, you will see that they are different. Still, carbon black performs better with no CO2 curing, but with 1% is kind of not much of a difference, and with 10% CO2 curing reference, it's the same, or even outperforms slightly, I would say it's the same than with recovered carbon black. So this is just showing you how the relative humidity during the curing process, during this just few hours that we do CO2 curing or not CO2 curing, change a lot the effect of the combined effect of CO2 curing and recovered carbon black. That's why it's so important to complete this matrix to finalize the model and see what are the best conditions. So how about comparing CO2 curing with no CO2 curing but high temperature curing? So here are some of the results. So here you have 0% CO2, so we are not doing CO2 curing, but we are doing high temperature curing compared to 20% CO2 curing. And we can see that we have the same or even slightly better results when we have CO2 curing, no heating than heating. So CO2 curing looks like it's a great option to not need to heat. So it's an alternative option, I would say. So yes, next steps, and I'm finishing because I know I'm getting out of time. We will complete this matrix, get all the data, and train the model to estimate the strength. Then we will do additional testing with intermediate values, with intermediate relative humidities and CO2 concentrations to test the model and to validate it. So then after that, we will just do TEA, SEM, and so forth to understand why this is happening. And then finally, I want to mention that we are undergoing the test also for corrosion resistance with different conditions. With that, these are just my references, and thank you so much.
Thank you, Miriam, so much for the great presentation. We have opportunity for the audience to just send the questions via text. So I can see already one question. Miriam, can you read the question? Are you able to see it? I can read it for you if it.
It's in the chat because, in QA, okay.
In Q&A,
yeah. I see it. So the question is, the carbon black increases the electrical conductivity and carbon steel forms a galvanic couple, thereby worsening the corrosion resistance of cement-based materials. I think more than a question is kind of a statement, which we will know soon because we are now in the process of doing the corrosion resistance of both CO2 cure concrete without carbon black and with carbon black. So we will see it. Now, having said that, as I mentioned before, all that we are doing is for precast elements, and not all precast elements are steel reinforced. One of the typical examples are pavers, which is a very important thing for us if we walk around here, right? And there are many others that are not steel reinforced. So one of the reasons why we are doing especially the testing with corrosion, the corrosion resistant testing, is just to test if what you are saying it is or is not in presence of CO2 curing. So I would say you might be surprised, but we will need to wait to see the final results. And again, it's true that corrosion is a concern when we are talking about carbon, right? And when we are talking about carbonation too. And that's the reason why we wanted to test it. And then you will see what is the limitations and the different applications where some of these technologies will work and the ones that we should not use it.
Thank you, Miriam, so much. Any other questions or follow-up questions?
I have a question.
Yeah, go ahead.
Somewhere in slide number 5 or somewhere in that area, you said that increase of strength and it reduces the porosity and water absorptivity. Throughout the presentation, I see all the data are very much experimental. Is there any general relationship between all these conclusive parameter or variables that we are talking of?
You mean when I was talking in the introduction?
Say, for example, your strength increases, it means by reducing the porosity or reducing the water content. Is there any relationship?
Yeah, well, when I say that, again, this is kind of a reference, this is something that is kind of in the literature, but CO2 curing increases the strength not only through reducing the surface porosity, but also by reducing the surface porosity. And then it's not reducing water content, is reducing water absorption. I can share the screen. So what I mean with that is just that when you have, let me try to share a screen if we have a minute. So I think you're mentioning this, right?
You are right.
Yeah, perfect. So yeah, there are several papers that mention this, and the main thing is that during the CO2 curing, you are changing the hydration itself. You are carbonating part of the belite that, if not, will not be reacting and so forth.
My question is there any mathematical relationship, any kind of threshold value, or is there any generic relationship? We know the result.
Relationship, no. There's no relation. Of course, there's always a relation between strength and porosity, right? You reduce the porosity, you increase the strength, but that's it. And now, of course, water absorption, I just mentioned that you reduce water absorption because that's very important, not just for the strength, but especially for durability. What happens is CO2 penetrates the pores, and especially in the first layer, what will happen is the CO2 will carbonate, also belite, some calcium hydroxide if there is already form and so forth. And because calcium hydroxide, calcium carbonate occupies more space than calcium hydroxide, you will have a reduction in the porosity. So that's pretty important for the durability side, because we all know that as the more water penetrates, the more issues we'll have with freeze and thaw, the more issues we will have also if we have salts with calcium oxide formation and other ones. So that's the reason why I mentioned that in the introduction, but again, that's kind of something that it is in the literature.
Okay, thank you.
Any other questions for Professor Velay-Lizancos? All right, thank you, Miriam, so much. Appreciate it. Thank you.
Thank you so much.
Move to the next speaker. Our second speaker today is Dr. Bhaba Sarker, who is an Elton G. Yates Distinguished Professor of Industrial Engineering at Louisiana State University. He obtained his PhD degree from Texas A&M University, worked with the World Bank, NASA, and taught earlier at UT Austin and Texas A&M University. He's a fellow of the Institute of Industrial and Systems Engineers. He won the IISE's National Award and the 2006 David F. Baker Distinguished Research Award for his outstanding research in industrial engineering. He's currently working in optimization, manufacturing systems and operations, supply chain logistics, construction management, and transportation logistics. I think he also might be joined today by his PhD student, Mr. Anik Mazumder, who might be giving part of the presentation today. So Baba, the mic is with you now.
Okay, thank you very much. Can you see my slide?
Yes.
Okay. Our background is industrial engineering. So we look at the civil engineering problem more from the operational and operational perspective, basically. So we are working on developing an internal integrated inventory system and the delivery plant of different precast material that comes to some industrial operations from where they make the PC and other materials. So that will be our main focus on the topic. And following that, we have some items that we'll be discussing. I will be talking on the beginning part of it, introduction on existing and research gap. And my student, Dr. Anik Mazumder, will pick up from the experimental part. So in the introduction part, we just look at what the PCs we are talking about from our industrial engineering perspective and the current existing facilities that we considered. Here in Louisiana, we have visited several of them, but 4 are more important. And of these 4, 3 construction firm, we just took as an experimental study. And from there, I will describe the problems. And we will find out basically what is the research gap we are finding. And from there, we will just follow different mathematical model and industrial applications. And these are the headings that we will see subsequently. Okay. So let's talk about what is optimized precast concrete supply systems. Here we'll be looking at different cost-effective and sustainable framework and how they are coordinated and how they are operating. And basically, it is a supply chain system starting from the raw materials, the procurement of raw materials, the manufacturing and production systems, then installation of the product that goes into the construction site. So these are the operations that we are considering. Our main constraint in this problem is basically the demand is not known all the time. Sometimes it is fluctuating. Also, because of the transportation or some other systems related to it, the lead time, which is basically the time to place an order and to get that order back to the positions, that is the lead time. And the lead time is also varying from time to time. So if we have this kind of scenarios, our demand is fluctuating, lead time is varying, and the materials is because of the time gap, the material sometimes is perishable. Then how do we handle that problem so as to minimize our cost as well as to enhance our desired results, which is the cost effectiveness or the efficiency of the systems, durability of the product, and those kind of things. Okay. And the second benefit out of it will be, then it will be high quality and durable product, which is basically the structural performance. Then with respect to process benefit, it will accelerate the constructions, just-in-time delivery. The moment it is delivered right on time, everybody is happy. Otherwise, both parties suffers economically as well as in time. Then systematic benefit is the enhanced durability. Then supply chain coordination, which will be very much improved. And our economic benefit out of it will be the cost savings, then efficiency of the system, and the sustainability of the product. Let's take some scenarios. These examples are coming from two of the examples that I mentioned about industries. One is Waski, another one is Gainis. These are some of the products. Their timely delivery and improved delivery. So, in this timely delivery system, we prevent the construction delays, and then structural performance, otherwise it will be late. Then coordination and workflow, coordination and the coordination in the material that they are manufacturing. These are the things that will be improving. On the other side, for improved coordination between production and the installation side, we will look at the delivery systems, then how do we handle the materials, then ensure the proper installation of the product and minimize the idle time. So that's what. So anyhow, we can save some time, save the product, then we save money, and both parties are happy, both supplier and as well as the user, which is the company that are using it. It could be government agencies or private agencies. In our existing systems, these are basically the scenario we look at it. So let's look at the raw material side. About 40 to 60% as per the NPCS reference. 40 to 60% of the total production cost is basically lying in the raw material side. When the raw materials are procured there in the production side, they are put as an inventory, and you can see the raw material inventory as just lying in front of them, which they are using. And once they are using for different types of product depending on the product, and once they supply, manufacture those products, and they deliver to the construction site. So that's basically our system that we are considering, from raw material, manufacturing site, and the using user site. Okay. So some of this raw material, that is improper coordination and vendor manufacturing, that is vendor who are supplying the material and manufacturer, there is not enough coordination, or not enough coordination, or because of some the variability of the demand, variability of the lead time, there is some kind of discrepancy between their communications. So other thing is the demand is not constant, as I mentioned. So the question is, how do we order them? And that's how do we place an order? How do we receive them? And given the condition that our lead time is varying from time to time. Okay. On the transportation side, so those are on the production or raw material side. Transportation side, we look at the delay of the PC product delivery to the construction site. Then uncontrolled expenses in transportation vehicle, that is another problem. Sometimes the crane is involved, that is another problem. Putting right on time and doing the right thing in right time, so that is another problem. The other thing is the scheduling of the product. Whatever operations are going, there are a lot of operations. I cannot show all of them here, but you can get some idea that what are different types of operations we have How do we handle them? How they are reliable? Even if we are handling, then how they are reliable? So all these factors basically accumulate to the cost, and that cost is to reduce, or time is to reduce. That is basically the whole goal of this system. So from the raw material, you can see right side, who is the construction side, the orders are coming for PC to the manufacturer. Then manufacturer place an order to the raw material, and then raw material comes. So when the raw material comes, then that raw materials you can see on the left bottom side, they are ordered or shipped at Q unit of time, Q unit of the materials at one time, and there could be some N operations. Like that, the raw material goes to the manufacturing site, and how much that Q or how much that is our one problem. And when it goes to the manufacturer, the inventory goes up, and depending on the demand situation, it will be fluctuating, and the inventory will be varying in the manufacturing site. Once it is this situation, then how do I minimize our inventory? Because any inventory coming to the any place in industry is a botheration, is money tied up with that, and no industry likes that kind of things. Okay. And then on the construction site, those materials comes up, this inventory fluctuate. So they experience both the material side and the manufacturer, both of them, they are experiencing. And that is the effect that we'll be looking at for the construction side, who are ordering, who are paying for it. And they will be looking at it, then how do I reduce the cost? How do we scale them? How do we order them? How do we transfer them? And those are the points that we will be addressing in this problem. I think I will be working up to this point, and Anik will be take over. He has done all this modeling and the analysis, so he will be better off to talk on these issues. So I will switch over to Anik, and he will look into the other materials that will be presented to you. Thank you.
Can you please? Sir, I think you have to stop sharing. Then I
Yes. Where do I do? I go to video.
You have to stop sharing on Zoom.
Sharing, just do it.
Okay, so can you see
it
my
okay?
screen?
Yes.
I think I have shared my screen. Can you guys see?
Yes, we can. Go ahead,
Okay,
please.
okay. Thank you so much. Thank you, Dr. Bhaba Sarker, for giving me the floor. I'll continue from here. In this graph, we can see that there are different types of probability distributions that are fitted for the demand and for different types and different scenarios of precast concrete components, which I have plotted here from our collected data. Also, in this image, we can see many more probabilistic variabilities for traveling time, which is actually the lead time for different types of precast raw materials, and also even the traveling time for different types of precast concrete components. And here another challenge is the perishability of various precast raw materials, which actually refers to the limited time span during which a material or a product remains usable. This may differ from one material to another, and therefore, if travel time of such
Anik, I think you're muted. Yeah.
Yeah, okay. So I think I video stop. So okay, so in this image, you can see that there are more variabilities for the lead time or travel times, which is for both for precast raw materials and also different types of precast components. And here another challenge is the perishability of various types of raw materials, which refers to the limited time span during which a material or product remains usable. This may be different for one material to another. So if a travel time of a certain material exceeds that shelf life, some intact material will become loose, and also moisture ingress can occur. And for that reason, binding strength may also reduce. So for such material, the price will exponentially be degrading. And if the manufacturer uses this product after their shelf lives, the lifespan of transportation infrastructure will be shortened. And also you can see here the unit price of such perishable raw materials are actually exponentially degrading from this image. And if a manufacturer uses this product and receives these raw materials after exceeding their respective shelf lives, and if they use these types of products to manufacture some precast concretes, then the main lifespan of some infrastructures, transportation infrastructures can be shortened, and also this will be then there will be more frequent maintenance and required traffic disruptions. So here we have developed two specific research objectives. So the first research objective is to minimize the integrated inventory cost of both precast material vendor or supplier and also the precast manufacturing facility. And to minimize the integrated cost, we have to determine the optimal ordering quantities, like how much a precast manufacturer should order for specific types of precast materials from the vendor. And also we have to develop an integrated cooperative policy so that the both parties are in the profit. And also we have to consider the demand as not as constant, but as a probability distribution, and also the traveling times or lead times. And also the perishability or the shelf life of precast materials have to be under consideration for our integrated models. And in our second research objective, we have to minimize the total cost of precast concrete delivery for a specific precast manufacturer facilities based on different types of demand scenarios for multiple construction sites. And here we have to determine the optimal number of shipments, and also we have to determine the optimal shipment quantities based on different demand and travel scenarios. So according to our first research objective, we have developed our integrated total cost inventory cost, which will be consisting of the total cost for the vendor and also the total cost for the manufacturer. Here, the probabilistic lead time tau will follow any kind of generic demand pattern, which can be any kind of probability distributions, and there will be a minimum and maximum range. Similarly, the demand will be following a probability distribution GD between two range D1 and D2. And also the nature of precast material will be time sensitive with a certain fixed shelf life, which is TS. And this whole big equation is the total integrated cost, which actually consists of the cost of vendor and the cost of precast manufacturer. Then we have proved and developed two theorems, like the first theorem: if the delivery lot from the precast vendor takes more time than the shelf life of that material for reaching to the precast manufacturer, then the vendor should be in fault, and also he has to bear the maximum cost burden. So therefore, if the delivery lot or delivery time exceeds the traveling shelf life, then the vendor's total cost will be bigger than the manufacturer's cost. And if the delivery lot arrives within the shelf life, then this function have to be strictly convex, from where we will be able to minimize this total cost by determining the optimal values of these three variables, Q, R, and N, where Q is the ordering quantity, R is the reorder point, and N is the number of shipments. So we have developed the formula for the optimal ordering quantity, and this is the formula. Here, in the denominator, we have three basic cost terms, which is actually the per unit holding cost of vendor, expected holding cost of the manufacturer, and also the per unit lost sales of the manufacturer. And the nominator, N, is consisting of these nonlinear huge terms. And also, if we are able to calculate the optimal ordering quantity, then we'll be obviously calculate the optimal number of shipments, which is this N star, and the optimal reorder point will be found from these iterative equations. So I will not waste any time to describe this kind of large formulas. So I'll go directly to discuss an industrial problem. And this industrial problem are collected from a typical precast manufacturing facility. But for the proprietary conflict, the data is changed a little bit. So for these values, we have developed and we have calculated our total cost for different scenarios, like for different number of shipments and different number of shipments. And here we have found that if the shipment number is 1 or 3, then the total cost, which are actually faced by the precast concrete manufacturing facility, and actually in this case study, the precast manufacturing facility ordered in 1 and 3 shipments, but this total cost for these two kinds of shipments are actually large and bigger than the shipment for size 2. So the PC manufacturing facility actually had to face the minimum integrated inventory cost when the number of two shipments were sent from the vendor to manufacturer. Like if the N is value 2, N is equal to 2, then obviously both the vendor and the manufacturer should have been in profit. So for that reason, our optimal values for this optimal ordering quantities, reorder quantity, and the number of shipments are given in this box with the minimized total cost for that particular case study. And we have performed some sensitivity analysis of these parameters by increasing and decreasing them by 25% or 50%. And these bold and blue values are actually the base values. And here you can see that the manufacturing cost is AM, I mean the setup cost for the manufacturer, and the AV, the setup cost for the vendor. So the setup cost for the vendor have more steepest slope than the setup cost of manufacturer, and that is because that the vendor has to consider the shelf life, and he has to take care of these kind of things, like he has to deliver the raw materials to the manufacturing facility before it exceeds the shelf life or the usability or lifespan for these typical types of raw materials. And we have also tried some random examples with different distributions of demand in different lead times. So you can see that the demand, we have applied some exponential distribution, uniform distribution, and normal distribution. Similarly, for the lead times or traveling time, we have so applied different types of distributions. And for all these variable case studies, we have developed our optimal values. And we can see when the both demand and traveling time are following normal or exponential distributions, the required CPU time is way higher. Now we will be discussing our second research objective, which was the precast concrete delivery modeling, in short the PCD model. And our first objective for this PCD model was to minimize the total cost by considering the optimal number of shipments, optimal shipment quantities, and also optimal shipment starting times, which will actually ensure the optimum scheduling for any kind of things. So this objective function will have lots of variables there. And this is actually a two-stage objective function that we will discuss later. So this objective function is consisting of the fixed vehicle contracting cost and fixed resource contracting cost. Also, these two parts are the fastest cost, like that will be calculated in the first test of the calculation. And for each sample scenarios or demand scenarios, this P to the power S is actually the probabilistic fraction for each scenarios, and this term is actually the scenario-based shipping cost. And this big term is also the scenario-based penalty cost for missing delivery deadline. And the last term is actually the penalty cost for unmet demands. And we'll have first stage and second stage constraints. So in the first stage constraints, we have ensured that the fixed cost of assigning vehicles and the vessels remaining in our budget, and also the resources are limited. So we have to ensure the allocation of resource very carefully. And in the second stage, we have to fulfill the demand of precast components in each project. And obviously, we'll have limited vehicles and vessels allocated for specific project, and we will have the limited capacity of these vehicles and vessels. Obviously, there will be timeline constraints for every project, and I mean, there should not be any kind of overlapping of two consecutive shipments for the same component in the same project. And obviously, there should be a delivery deadline for delivering one precast component from one place to another. And such similarly, like the constraints, we will have first stage decision variable, and these are the decisions that are made before knowing the scenario-based values like demand or travel times. And these there will be some second stage decision variables, like how much tons of precast concretes from one batch to another batch we will have to shift through one specific mode of transportation in scenario and in specific scenario. And so these type of decisions will be taken after the realization of uncertainty of every scenarios. And then we have tried to apply another industrial problem for this project. So this illustrative data set actually covers a small portfolio of 10 road projects consisting of 3 batches of 5 types of specific precast concretes. And we have 3 modes of transportation: the flatbed truck and barge and also rail. And here we will have 100 numbers of randomly sampled demand and travel time scenarios. Here demands are randomly distributed from 50 to 80 tons per product in each scenarios, and also the travel times are distributed in 3 to 10 uniformly in every scenarios. So here will be our 2-stage decision model. First, we will try to calculate the optimal number of vehicles and the resources, and then we will have to have the expected penalties in our every scenarios. So in each scenario sampling, we have calculated the resource cost, approximated resource cost, but we didn't apply and we didn't calculate for the 100 scenarios at a time. So we first have 20 or 30 sample scenarios, and then we have computed the sample scenarios by doing some greedy batch assignment to every mode. Like the greedy batch assignment means that we have to ensure maximum number of loads of precast components should be allocated to each mode. Like we will not lose any kind of space or capacity. And then we will have to make sure that unmet demands and delays are satisfied. And obviously, then we calculated the average penalty for these 20 samples from this 20 randomly selected samples from the total 100 samples. And this was the cost convergence curve. And here we have applied the genetic algorithm operators here. So we have initialized 30 random integer vectors within the vehicle or vessel resource bounds. Obviously, there are bounds of the number of vehicles and vessels, and also the amount of capacity. And then we selected some parent solutions, because this objective function is not a traditional convex objective function. So we'll have to select, and we have to start from any parent solution. And then we have performed some mutations and some duplicate eliminations. And then we have terminate our calculation process after 50 generations by returning the optimal result. So here in the same convergence curve, you can see like in the first 1 to 600 values, function 600 iterations, there was a rapid improvement, like the cost was converging rapidly. But from 600 to 1,000 evaluations, the cost was kind of constant, and there was a sudden drop. And then afterwards, there was no change at all. So we can pick this value as our optimal solutions. And this curve is actually for the rail reallocation. Like this was not for all the vehicles. And when we perform similar process for all the vehicles and all the scenarios, we have calculated that we will need 12 flatbeds, 9 barges, and 6 rails. And this will be our optimal vehicle mix. Like we will have to use our trucks for total 44.4% time. 4% to satisfy 4% demand. And the ratio for the barge will be 33.3%, and the rail will be 22.2%. And this was the other resources like cranes and then all the stops. So this was the units, that optimal units that we got. And this curve was actually the final solution performance across the 100 scenarios, because previously we have shown that we selected just 20 random samples from these 100 scenarios. So this is the curve distribution. You can see it's kind of a normal, but skewed to the left or right. And this is the worst scenario. Worst was the $85.06 million. And the best performance was the $79.67 million. And there was a standard deviation of 1.12 million. So this part of our research is actually still in under progress, and we will try to apply other algorithms to look for the better results. And if we just summarize all of the results, we have developed an optimal order and reorder quantities to minimize the total cost for both main vendor and manufacturer. We handle different generic distributions for demand and material traveling time, also traveling time for the components. We minimize the precast concrete delivery cost, where we have captured shelf life behavior of different types of precast materials in our optimal policy. So as managerial aspect, we have optimized raw materials right now. We can avoid overstock and reduce the storage cost. We can reduce the project delays and also assess the cost impact from different types of demand and lead time shifts. So in our future work, we'll consider more batch production system considering raw materials conversion factor, and also we will consider more general scenarios and algorithms for transporting components, and we will consider disruption in the pathways of each type of transportation modes. Like the disruptions type of rail will not be the similar from disruption type that you can face on road. So we will consider them, and also consider some disruptions in construction and installation process in our future modeling. So we have already submitted 2 papers in our Journal of Construction Engineering and Management, and also the Journal of Production Economics. And this is the list of the submitted quarterly progress reports. And these are the references that we have used. And thank you, everyone. If you have any question, please.
Thank you very much. Very, very nice presentation. Very, very nice work. We have time for maybe a couple questions. You guys can type the questions if you want. Meanwhile, I can maybe ask a quick question. Now, the problem, of course, that you are trying to address here is quite complex problem. We have to agree on that. So there is really, very hard way that you will satisfy the audience simply by showing these mathematical equations without any practical, application, because every project is unique, right? And projects, although they have some precast components, only that is a part of a bigger picture. It's only 1 or 2 phases of the project that has precast component. Everything is really interconnected. It would be, advisable in the future maybe to start looking into this piece and how it connects to the bigger, in the context of the bigger project. For example, when we talk about the bridge, bridge decks usually are cast in place. However, the girders could be precast. So, and they are somehow connected. And the schedule of the project, because one of the concerns you have is the delays, the schedule of the project could also be connected to the delays encountered in the cast in place, which, whether we like it or not, affect the precasters' scheduling. So that's an important thing. Another thing also that I would just comment on here real quick is your way of laying out the results, I think, is like more of an abstract way, like very, we don't know what type of components. When we say a 50-foot long box beam is one thing, and when we talk about 150-foot long, bulb T girder, that's a completely different component. Transportation-wise, complications when it comes to delivery or installation-wise, and these are all comes into play. So I don't know, I'm not saying that you have to answer this now, but something to think about ahead if you continue in this direction of research, that you might want to think about maybe showing or applying this on one or two examples of actual bridge components. For example, if you are aiming at bridges or precast pavement, if you are shooting for precast pavement or any other components like, barriers, for example, if that's part of what you're doing, and just apply these theoretical, formulas on it, with working with one precaster to see, how this applies, without having to reveal. Of course, a lot of precasters, they have their own proprietary, information that they don't want to share. But again, within whatever you're able to, get from them and work with them on this, that will make it a little bit more meaningful and practical. If you want to comment on this, or if you have anything to say about that.
I would like to add a point. Yeah. So this is our second research objective that I just showed. It is still under progress. So we are actually using some specific real life project data here. So when our model, the final model and result will be in our hand, we'll obviously show then how this, obviously, if you want to construct any kind of bridge, so every component of that bridge will not be precast. So we will actually show like what kind of precast components are delivered through what kind of transportation modes in what amounts, and to procure and to manufacture that component, a precast component, that precasters have to order how much materials from which vendor. So we will then obviously show show some graphical and mathematical representation of these things. But thank you for your suggestion. That was a very valuable suggestions.
Okay, I'm glad to hear that. Very good. Any other comments or questions from the audience? All right, if that's the case, then thank you so much. I would like to thank the speakers again for their valuable time and the great presentations. We appreciate very much. I would like to thank the audience for their time as well, and we will be looking forward to seeing you all the next time, our next webinar. Have a great weekend, everyone.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Thank you very much.